Tape to HST. Okay, thanks.
In the ongoing exploration of our universe, every journey begins with the eye. Only the eye can travel to the stars and beyond, far outpacing the meager reach of any human astronaut or probe. Chasing the ancient light of distant galaxies back to the dawn of cosmic history. In this epic journey of discovery, no eye been more revealing and more awe-inspiring than the Hubble Space Telescope.
Start moving out. Copy, P3.
We're stalling minus 0.05 at 100.
The Hubble is not the largest telescope ever built, but it is the first large telescope ever to fly in space. This unique vantage point, high above the blurring effects of Earth's atmosphere, is the perfect perch for exploring everything from nearby planets to distant galaxies. Unlike telescopes on Earth, the Hubble can't be maintained and improved on a routine basis. Astronomers can't just drive to the Hubble to give it a tune-up. Instead, the telescope depended on visits from the space shuttle and its crew to make repairs and install new cameras. This is not an easy task, and missions to the Hubble have been among the most challenging and exciting in the history of human spaceflight. And then, on February 1st, 2003, disaster struck. The space shuttle Columbia was lost, taking the lives of 7 astronauts. Columbia's mission was not related to the Hubble, but its loss was to have a profound impact on the space telescope. After the accident, the remaining space shuttles were grounded, which postponed a 5th and final mission to bring new cameras and replacement parts to the Hubble. Two years later, even with new safety measures in place and the shuttles heading back into orbit, the Hubble repair mission was officially off the schedule. The reason was human safety. The Columbia disaster demonstrated how dangerous a space shuttle mission can be. Hubble's supporters were deeply disappointed. Without human support, it seemed Hubble's great eye on the universe would close forever. The telescope would slowly shut down and, in time, come crashing back to Earth. But scientists asked NASA to reconsider its decision. Flight engineers began working on scenarios that would involve one shuttle going to the telescope with another one ready on the launch pad in case of a problem. And by late 2006, with confidence in the shuttle program restored, NASA was ready to try to save the Hubble. The job would not be easy. During the years that the shuttle was grounded, the Hubble was showing signs of age. Its cameras were malfunctioning. Batteries and gyroscopes that were essential for powering and pointing the telescope were failing too. As engineers began to visualize the sequence of repairs that would be needed to restore the telescope to its full operations, it soon became clear that this would be the most ambitious mission to the Hubble ever attempted. A giant pool with a full-sized mock-up of the Hubble was used to simulate the weightlessness of space. Hubble's new parts were brought out of the clean room and readied for launch. They included a pair of new cameras designed to transform the space telescope and image the universe as never before. The Wide Field Camera 3 is a versatile multi-wavelength detector capable of imaging distant objects across a broad spectrum of colors. Also on deck was the Cosmic Origins spectrograph, designed to use the light of distant sources as a way to probe the large-scale distribution of matter throughout the universe. Finally, on May 11th, 2009, the rescue mission was underway.
7, 6, 5, 4, 3, 2, 1, and liftoff on Space Shuttle Atlantis. Final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Bypass across the board, Scooter, no action.
Houston Atlantis for Star Tracker.
Scooter, go ahead for Star Tracker.
We see that star approaching from the east.
Hey, that's terrific news. I guess the last time we've seen Hubble up close was March of '02.
From Houston Atlantis, 200 feet.
No previous servicing mission had ever demanded so much of astronauts in such a short time.
Houston Atlantis. Hubble has arrived on board Atlantis with the arm.
By now, it was more than 7 years since someone had visited the telescope, and the Hubble was badly in need of attention.
Coming out. Yeah, I'm just looking out the window here, and it's an unbelievably beautiful sight. Amazingly, the exterior of Hubble, an old man of 19 years in space, still looks in fantastic shape.
Installing the wide field camera was challenging but straightforward.
Counterclockwise, 2.
The new camera was built to fit neatly into the space left by its predecessor.
Look good? Looks good to me. I definitely got it. Excellent.
The Cosmic Origins spectrograph fit into another space, previously taken up by a device once used to correct the built-in flaw in Hubble's optics.
Coming in now.
Okay. And another inch down.
One more inch down.
This one feels different.
All of Hubble's new instruments now correct the optics automatically.
This one feels like it won't sit flush on the plate.
What kind of curves do you think Hubble will throw at you? I don't know. It's been Dave surprises each day.
Maybe no more away, right only.
The most challenging fix of all was to Hubble's advanced camera for surveys. Since it was installed in 2002, the ACS had created some of Hubble's most spectacular images.
Takes a few more turns to get it
But
out
a
of the
short circuit knocked out the camera after 5 productive years. Now astronauts would try to get it back.
Third one is out. Nice. I heard that. Thank you, great, John. Nice job.
Nice job, Tom.
Incredibly, the repair went without a hitch. The ACS was back online, and with the replacement of batteries and gyroscopes as well as other repairs completed, the Space Telescope was ready to return to work. It was time to say goodbye to Hubble.
Flight controllers off.
Oh, baby, look at that.
What a beautiful spaceship we're on, guys. It's a real privilege to get to see what we're seeing and get to work on this magnificent machine. Hubble isn't just a satellite. It's about humanity's quest for knowledge. As Arthur C. Clarke says, the only way of finding the limits of the possible is by going beyond them into the impossible.
No one would ever see the Hubble this close again. What astronomers would see through the Hubble's new and improved cameras was yet to come. Like a dandelion adrift in a field of stars, a small, cloudy patch of light in the southern constellation Centaurus draws the eye. This is Omega Centauri. Located some 16,000 light-years from Earth, it is a vast congregation of stars known as a globular cluster. It formed more than 10 billion years ago and now moves through space like a cloud of fireflies as it orbits the center of our Milky Way galaxy. For astronomers, globular clusters are like laboratories, tailor-made for studying the evolution and dynamics of stars. That made Omega Centauri an ideal target for testing the new power of a restored Hubble Space Telescope. In this image, taken soon after Hubble's dramatic repair in May 2009, the telescope's new wide-field camera peers through millions of stars to reveal the cluster's sparkling heart. The stars' dazzling colors offer a clue to their history. As expected, most are yellow or red, indicating these stars are entering their old age after shining for billions of years. But the blue stars, which are much hotter, seem a mystery because blue stars should be very young. Astronomers now suspect some of these blue stars are the result of stellar collisions and mergers. The amazing clarity with which Hubble can view these stars also gives astronomers a window into the future. By comparing this image with earlier images of Omega Centauri, Hubble can see that the stars have moved. And by extrapolating those motions, astronomers can simulate a 10,000-year timeline, showing how the stars will migrate as each follows its own course. Since Hubble was first launched, one of its great achievements has been to reveal in stunning and colorful detail the complex cycle of life and death among stars. Now, with its new wide-field camera in place, Hubble is showing us this process as never before. Here we see in the death of a single star a celestial metamorphosis. Its energy spent, the star has blown off its outer layers, forming what looks like a cosmic butterfly. The details in this image reveal that stellar death is a multi-stage process, with gas ejected at different times and at different speeds to form a remarkably complex shape. The details are important because the material ejected by dying stars is ultimately what will be recycled into new stars and new solar systems, including some with planets capable of developing and supporting life. Elsewhere, in the Carina Nebula, Hubble spies the fiery formation of new suns inside a vast and churning cloud of interstellar gas and dust. 7,500 light-years away, this is one of the brightest and most spectacular star-forming regions in our neck of the Milky Way galaxy. As Hubble zooms in, a blazing tapestry of glowing gas gives way to a more detailed look at a single pillar of dust, 3 light-years long, nestled within the nebula. Powerful stellar winds are gradually eroding the pillar, which acts as a cocoon, protecting a cache of newly formed stars and planets within. With its infrared capability, Hubble's wide-field camera can peer inside the Carina Nebula and reveal hidden details. Here, the infrared view reveals high-speed jets of ionized gas, which point back to a newborn star within the cloud. The jets are a telltale sign of stellar birth, and they signal the arrival of a new solar system on the cosmic stage. Peering out at the Large Magellanic Cloud, a companion galaxy that orbits the Milky Way, Hubble can see the entire pageant of stellar birth and death in one image. This is the Tarantula Nebula, one of the most active star-forming regions found anywhere in space. Here, a cluster of freshly minted blue supergiant stars light up a vast complex of interstellar gas with their intense energy. Many of these stars are burning so ferociously, they will one day be gone as quickly as they came, exploding as supernovas bright enough to be seen on Earth without a telescope. In the process, they will cook the matter in their cores, spewing out the heaviest elements in nature like iron, nickel, gold, and silver, enriching the Large Magellanic Cloud with the same kinds of atoms that, in our galaxy, have been crucial to the development of civilization. With its improved powers of perception, the Hubble has again become the best way for astronomers to trace the ebb and flow of atoms in our own galaxy. But what Hubble is ideally built to do is tell us a story on a grander scale, the birth of the galaxies. That's why, once Hubble's vision was restored, astronomers were keen to point the telescope out to the farthest reaches of space. Before the Hubble, the youthful days of our universe were off limits to astronomers. Of course, it's possible to look back in time simply by peering far off into space. Because the light from distant galaxies needs time to reach us, we can see those objects not as they are today, but as they once were long ago. The trouble is, even looking at galaxies that are millions of light years away isn't enough to see what the universe was like at an earlier stage, when astronomers think most galaxies formed. To do that, a telescope needs to look back about 10 billion light years, and Hubble has been doing just that. Some of the best views of this elusive period come from the Hubble Ultra Deep Field, a sampling of the universe at the very limit of Hubble's perception. To achieve the Ultra Deep Field, Hubble literally spent days staring into empty space. As the extremely faint light of distant galaxies began to build up on Hubble's sensitive detectors, an astonishing picture of the early universe began to emerge. What Hubble found is that at these great distances, galaxies tend to be smaller and more distorted in shape. This tantalizing result means that Hubble is beginning to see back to an era when the galaxies were still forming, mere adolescents on their way to becoming the grand star systems we see today. Since its repair, Hubble has returned to the ultra-deep field and again gone diving into this cosmic well, this time using the infrared capability of the Wide Field Camera 3. The effort has yielded Hubble's most distant finds to date, a handful of tiny galaxies that appear to be a staggering 13 billion light-years away. This not only breaks a record, it tells astronomers that the earliest galaxies must have formed quickly, already springing into existence before the universe was 5% its current age. With this incredible feat, the reborn Hubble Space Telescope has now put us on the threshold of the birth of galaxies, one of the great milestones of cosmic history. To actually see the galaxies being born, astronomers know they'll have to go one step further, and another space telescope will have to get them there. Currently, the James Webb Space Telescope, Hubble's direct successor, is scheduled for launch in 2018. By then, Hubble will have finished its long and incredibly successful mission. Rarely has one instrument done so much to change our understanding of the universe. With its newly restored and improved eye on the cosmos, Hubble is not only becoming a legend in its own time, it's setting the course for the next era of cosmic discovery. It has been more than 4 centuries since human eyes first gazed at the heavens through a telescope. Since then, the telescope has transformed our understanding so deeply, it is almost as though the universe itself has changed before our eyes. The wandering planets, once no more than bright lights in the sky, have become entire worlds, each with its own unique features. Faint patches of light have morphed into spectacular nebulas, where new solar systems are born by the thousands. Or giant galaxies gracefully flying through the cosmos, millions of light years in the distance. The universe itself has proved to be far larger and more ancient than our ancestors ever imagined. In this century, 2 questions have set the course for our telescopic exploration of the universe. The first is about the origins of the universe itself. How did all of this get here? And what are the conditions that allowed the universe to evolve from an initial explosive event, known as the Big Bang, into its present form, with stars, galaxies, black holes, dark matter, and more. The second question has to do with our own origins and whether the conditions that led to our emergence here on Earth are common enough elsewhere in space to allow us to find other worlds harboring civilizations like our own. The tools that will allow astronomers to get at these questions are nothing short of extraordinary. They are telescopes, but telescopes larger and more penetrating than any ever built. Some will be built on Earth. Others will orbit in space. Together, they will allow us to see farther than humans have ever seen before. To understand how, consider the Hubble Space Telescope, currently astronomers' state-of-the-art instrument for exploring the universe. The Hubble is really a sophisticated light catcher. It uses its giant primary mirror to grab as much light as it can from distant objects and then focuses that light to produce an image. Looking far beyond the stars of our own galaxy, Hubble's big mirror catches enough light to see very faint galaxies billions of light years away. But galaxies quickly become fainter and are invisible to Hubble beyond this point. So to see more and see farther, astronomers are developing the James Webb Space Telescope. This is a light catcher par excellence, with a primary mirror that covers 6 times the surface area of Hubble's. Any telescope that big is certain to take astronomy to a new level. But getting such a giant into orbit is no small feat. For starters, it's already too big for any rocket to carry. That's why, instead of a single primary mirror like Hubble, the James Webb Space Telescope will use 18 smaller, precisely aligned mirrors that will connect together like a honeycomb after the telescope is launched. These smaller mirrors are also easier to produce and lighter to carry into space. But size alone is not enough. Even with a big mirror like this, the universe makes the most distant galaxies nearly impossible to see. This is because the expansion of the universe pulls the galaxies away from us and shifts their light toward the red end of the spectrum. The very farthest galaxies have been shifted so much they shine not in visible light, but in the infrared. So, to have a hope of seeing even further than Hubble, the James Webb Space Telescope will be tuned to see the heavens in infrared light. This is perfect for observing the distant universe. And it has to be perfect. Because unlike the Hubble, which is much closer to Earth, the James Webb Space Telescope will be too far away for astronauts to reach. That means the telescope will have to work all on its own, with no hope of repair if something goes wrong. Technicians are carefully assembling the telescope. When it's ready, it will be folded up like an elaborate umbrella and launched into space. After a month-long journey, the telescope will unfurl. Slowly and methodically, the various components will unpack themselves. The sunshade will unroll, and the solar panels, much larger than Hubble's, to compensate for a more distant and weaker sun, will deploy. Finally, the gold-coated segments of the mirror array will open like the petals of a flower and click into place, ready to direct light into the telescope's detectors. All that will be left to do then is to look and let the universe reveal itself. The launch of this ambitious telescope will be a major achievement, but it will only herald the start of a new era. To see where that era will lead us next, our quest for bigger and even better telescopes will bring us back down to Earth. Perched on lonely mountaintops in distant corners of the globe, the world's great astronomical observatories seem to exist between two realities: the terrestrial and the celestial. The largest observatories are finely honed operations, more like astronomy factories than lonely outposts. They use sophisticated optical techniques to help cancel out the effects of Earth's atmosphere. As a result, the biggest telescopes on Earth have come to complement and rival the Hubble telescope in space. But now astronomers have come to the limits of what the largest observatories on Earth can see. To see the birth of the galaxies and to look for planets forming around other stars, the next generation of telescopes must be larger, far larger than anything ever built. Today, 3 projects are leading the way, setting the stage for the next wave of great observatories. Each has its own unique design and location, but all will be built to address the same underlying need: collecting as much light from the distant universe as possible. This is a technical challenge of the highest order. For the giant Magellan telescope, the answer is to combine 7 of the largest mirrors possible and hold them together so they can operate as one single supermirror, 24.5 meters across. Like an alien flower, the giant Magellan telescope will turn its petals skyward to gather starlight from the summit of Las Campanas, a spectacular mountain location in Chile. The estimated cost is $700 million. Pushing the limits even farther, a consortium of nations is planning the TMT, the 30-meter telescope. At a cost of $1 billion, it will be built on Mauna Kea and dwarf the other large telescopes that already crowd Hawaii's tallest mountain. Unlike the giant Magellan telescope, the TMT will not consist of a few large mirrors working together. Instead, following from the design of the nearby Keck telescope, it will view the heavens with a mosaic of 492 mirror segments, each just over a meter across. So equipped, TMT will be able to pursue its key goal of investigating the early universe. From the birth of the first stars to the formation of the galaxies. An even larger telescope is now being planned by the European Southern Observatory in Chile. It's called the EELT, short for European Extremely Large Telescope. Like TMT, it will also use a segmented mirror, but in this case made up of nearly 1,000 individual segments, all fitting together to create a light-gathering surface that is a whopping 42 meters across. At an estimated cost of $1.4 billion, this would be, by far, the largest telescope ever constructed. It will be located on Cerro Armazones, one of the most promising locations in Chile, and perhaps the best mountain in the world that does not yet have a major observatory on it. But the EELT will far exceed previous telescopes in its ability to see the early universe. Its instruments will also specialize in identifying the signatures of different chemical elements, helping to identify the ingredients from which the first stars and galaxies were made. As well as look for signs of molecules important for life in the atmospheres of planets around other stars. All three of the new giant telescopes could be in operation by 2020, though this will depend on funding. The plan is they will work together with and follow up on discoveries made by the James Webb Space Telescope. They will also be engineering and scientific marvels, monuments to our innate desire to learn about the universe around us. But above all, they will be doorways to future understanding. The tools that will help us discern hidden clues to the nature of the universe and the riddle of life, and point the way forward into the infinite unknown. The next generation of telescopes, both on Earth and in space, promise to help answer two of the most important questions we have ever asked about the universe. Where did all of this come from? And are we alone? These questions are not new. What is new are two surprising finds that suggest exciting answers may lie just out of the reach of current technology. These findings are now helping fuel the push for new instruments of astonishing size and ambition. The first surprise is the discovery of dark energy, a term that astronomers have coined for something they barely understand. Simply put, dark energy is a property of space itself. It seems to exist everywhere, and yet cannot be measured directly anywhere. It was discovered by looking at a type of supernova, a brilliant explosion that is triggered when a massive star starts pouring vast quantities of hot gas onto a small, dense companion known as a white dwarf. Once the burden on the white dwarf reaches a critical limit, it becomes unstable and suddenly erupts, generating enough light to outshine an entire galaxy. Then, by comparing both the motions and the distances of many supernovas, astronomers can see if the expansion of the universe has changed over time. When researchers first started doing this in the 1990s, they made an astounding discovery. The expansion of the universe is speeding up. That means most of the galaxies we observe are moving away from us and from each other faster and faster as time goes on. Something is causing this to happen, and that something is dark energy. One new telescope is ideally configured to probe this mystery. It's called the Large Synoptic Survey Telescope, or LSST. While it's not as large as some of the other future telescopes currently on the drawing board, the LSST will have the largest field of view of any telescope its size. Specially designed for a wide-angle perspective, it will take in vast swaths of the heavens all at once, managing to image the entire sky twice every week. All of this data will allow astronomers to look for and measure the effects of dark energy in multiple ways. Those measurements will help distinguish between different theories for what dark energy is and how it works. Theories that can eventually be tested by the much larger telescopes to come. The other question motivating the development of new telescopes is one that goes to the very heart of our existence. We know, because we are here, that life is possible. What we don't know is how likely life might be, and whether the odds favor us eventually making contact with other civilizations on distant worlds. One way to address that question is to find other places in the galaxy where life could be. That's why the discovery in the 1990s of planets orbiting nearby stars electrified astronomy and captured the public's imagination. So far, none of these planets share exactly the characteristics of Earth, including size, composition, and temperature. But NASA's Kepler spacecraft, currently in orbit, is capable of detecting other Earths. And when it does, larger telescopes will be needed to follow up. Astronomers are now considering how best to create a new kind of orbiting space telescope that will be able to zoom in on the other Earths that Kepler finds. To succeed, such a telescope will likely be both large and complex. Its job will be to tease out the faint light of an Earth-like planet from the billion times brighter light of the star it orbits. If it succeeds, that light can then be analyzed for signs that there are biologically important molecules in the planet's atmosphere, like oxygen or water. Just a generation ago, astronomers would have thought such a feat virtually impossible, but it may only be a decade or two away. In the end, it is our curiosity about ourselves and our desire to find others like us that will drive the development of telescopes to even greater heights. With the telescopes of the future extending our vision even farther into the cosmos, it seems there is no end to what we may see. In our ongoing desire to comprehend a vast and mysterious universe, seeing is not just believing, seeing is everything. While we experience life on Earth using all 5 of our senses, in space, virtually everything we know about the universe comes to us through our ability to see. We gather up the light of the stars and galaxies with our telescopes, and by analyzing that light in a multitude of ways, we gradually unlock the secrets of the cosmos. The invention of the telescope changed our understanding of the universe forever, because it allowed the human eye to overcome a natural barrier and see objects that are much fainter and farther away than we would otherwise see. But there's also another barrier that limits what we can perceive when we look out into space. A barrier that can be overcome if we can learn how to see the universe through very different eyes. That second barrier exists because what we experience as light is really a wave of energy. And whether we can see it or not depends on the length of that wave. The human eye can only perceive light waves that range from about 39 to 75 millionths of a centimeter long. That narrow range, known as the visible spectrum, includes all the colors of the rainbow. But where the eye stops, the spectrum of electromagnetic waves, of which light is just one small part, continues. Now, the opening up of that spectrum at many other wavelengths has given astronomers a cosmic rainbow of new possibilities to explore. It began with radio waves. For decades after radio was invented, no one thought it would be possible to receive radio waves from space. Then, in 1931, an American engineer proved that idea wrong. Carl Jansky was working for Bell Telephone Laboratories, trying to identify natural sources of radio interference that might affect transatlantic communications. With a special receiver set up in a New Jersey field, Jansky found a mysterious hiss coming from the sky. Jansky discovered the radio hiss was always strongest when the Milky Way, especially the bright central region of our galaxy, was above the horizon. Something toward the center of our galaxy was producing radio waves. And there were other sources too. An entire radio universe just waiting to be explored. But what kind of universe would the new technology reveal? Looking at the sky through radio eyes, our entire Milky Way shines with the cool glow of hydrogen gas. Even parts of the galaxy that are blocked from our view by thick clouds of interstellar dust can be mapped in this way. Astronomers have used this convenient fact to uncover the spiral structure of the Milky Way. And radio waves can also help reveal more energetic phenomena. A supernova, the explosive death of a massive star, and one of the most spectacular sights in the universe. For centuries after the event, a bubble of energized atoms expands outward, the far-flung remains of the obliterated star. As the supernova bubble crashes into the surrounding interstellar gas, it gives off radio waves, creating what looks like a bright wreath of radio energy. A black hole is formed when matter is squeezed to infinite density, creating a bottomless pit in space. Once inside, not even light can escape the black hole's irresistible pull. On the way in, gas and debris swirl ever closer to the edge of the black hole. Some of this gas manages to narrowly escape and instead feeds massive high-speed jets of electrically charged particles, which fire outward along the black hole's axis of rotation and become strong emitters of radio energy. Today, astronomers know the radio waves emanating from the center of our galaxy, the same signal Carl Jansky first discovered, come from a giant black hole as large as a solar system. And the Milky Way is not alone. Thanks to radio telescopes, it's now clear that most galaxies contain monster black holes, sometimes with active jets, which are among the strongest sources in the radio sky. Seeing the universe through radio eyes has given us a new perspective, allowing astronomers to discover and study phenomena that were once completely unknown. But radio is just the beginning. There are many other ways to see the universe, especially when we leave Earth behind and begin to observe with new eyes in space. The universe that is most familiar to the eye is the universe revealed by light. As stars and galaxies shine across the vast reaches of space, their subtle colors carry important clues about temperature, chemical composition, and distance. But all the colors of light we can see are just small parts of a much larger spectrum that stretches out well beyond the range of human vision, from very long to very short wavelengths. At wavelengths shorter than the human eye can see, light transitions into other forms of energy that can only be detected with special sensors. And because it takes a lot of energy to produce them, these shorter wavelengths, like ultraviolet, X-rays, gamma rays, are ideal for studying some of the most energetic and most violent phenomena in nature. The catch is that Earth's atmosphere blocks most high-energy forms of radiation. That's good news for life on Earth's surface, which depends on the atmosphere like a protective blanket. But it also means astronomers need to get their telescopes off the ground if they want to explore the high-energy universe. The Hubble Space Telescope makes an ideal starting point. Its cameras see what our own eyes see. But by using special filters, astronomers can also zero in on the hotter, ultraviolet part of the spectrum. By showing only the very hottest stars, Hubble gives astronomers a chance to peer deep into a galaxy's core. Another telescope, the Galaxy Evolution Explorer, or GALEX, is dedicated to looking for sources that shine bright in ultraviolet light. These are the most energetic and short-lived stars we know, and astronomers believe they may hold clues to how the galaxies formed and evolved. That's because the hottest stars we see today may resemble the very first stars that formed when the universe was just a small fraction of its current age. When those stars died, their cores collapsed to form black holes. And some theories suggest the black holes merged to form even larger black holes like those we see at the centers of galaxies today. Galax has also found other ways to bring hidden details about the stars to light. For example, the aging and bloated star known as Mira is too red and too cool to be observed in the ultraviolet. But Galax has found that Mira is generating a wind of high-speed particles, which smash into the surrounding interstellar gas, creating a glowing tail that reveals the star's movements for the past 30,000 years. Leaving the ultraviolet behind, the Chandra X-ray Observatory is our guide to an even higher temperature X-ray universe. To collect X-rays, Chandra uses a series of 4 nested cylinders coated with iridium to reflect and direct the X-rays into a sensitive detector. Only objects with temperatures of millions of degrees are able to produce X-rays through heat. Here, a supernova that was witnessed by the astronomer Tycho in 1572 appears like a frozen fireworks display when seen in X-rays. One of the most spectacular sights in the X-ray universe is this stunning panorama from Chandra, showing the region near the center of our Milky Way galaxy. This area is hidden from optical telescopes by dense clouds of interstellar dust. But X-rays, which pass right through the dust, unveil a chaotic spacescape full of churning hot gas and bright specks that could signify where neutron stars and black holes are devouring companion stars. At the very heart of this fascinating region is a bright cloud of gas surrounding what is thought to be the location of the Milky Way's giant central black hole. When combined with a view in infrared light, Chandra's X-ray image is our most revealing glimpse yet of the most extreme location in our galaxy. Looking beyond X-rays, astronomers have also begun to explore the universe at even shorter wavelengths and higher energies. NASA's orbiting Fermi telescope is designed to detect gamma rays. Fermi registers their arrival as they rip through canisters filled with metal plates and split into pairs of matter and antimatter particles. This design allows Fermi to deduce the energy and incoming direction of the gamma rays. One of its most surprising results has been the discovery of 2 giant bubbles of energetic particles emanating outward from the center of our galaxy. The cause of these bubbles, each 25,000 light-years tall, remains unknown. They could be linked to outbursts from the Milky Way's giant black hole. Even more perplexing has been the mystery of gamma-ray bursts, vast explosions that appear all over the sky at great distances, far from our own galaxy. Astronomers believe they may mark the births of black holes from the collapse of massive stars. Perhaps only the Big Bang itself can top an event as powerful as a black hole's birth. But to look for evidence of the Big Bang, astronomers must change perspective yet again and see the universe in a different light. The more we can expand our vision beyond what the eye can see, the more we can learn about the universe. Even in the narrow range of light that the human eye responds to, small differences in color can yield great storehouses of information. Here, with this magnificent view of the Whirlpool Galaxy, over 30 million light-years from Earth, the Hubble Space Telescope plays witness to a great cosmic cycle. The giant spiral waves sweeping through the disk of the galaxy show where vast clouds of hydrogen gas, triggered by gravity, are collapsing to form new stars. The stars light up the gas, which gives off a pink light. In comparison, stars are not forming near the galaxy's central region. There, a population of middle-aged stars gives off a cooler, yellower light. But now, as seen through an infrared camera on the Hubble, we find the galaxy is threaded through with glowing wisps of interstellar dust. The particles that make up the dust are tiny, like smoke. But collectively, and through infrared eyes, they reveal what is going on below the threshold of human vision. Infrared telescopes offer astronomers a way to probe the cool universe at wavelengths longer than the human eye can see. Since the atmosphere blocks most wavelengths of infrared, the telescopes that are best able to exploit this part of the spectrum are in space. The Spitzer Space Telescope is sensitive to the infrared light that is nearest to visible light. With the Spitzer, many celestial objects look familiar, but also just a bit different. Here, the North American Nebula gets its name from bright and dark clouds of gas and dust that vaguely resemble the familiar outline of the continent, complete with the Gulf of Mexico. But using Spitzer's infrared vision, the dark regions suddenly light up, revealing the structure of the dust clouds. Pushing farther into the infrared universe is the Herschel Space Observatory, currently the world's largest orbiting telescope. Herschel looks at longer wavelengths than Spitzer, so it sees even cooler objects. Its specialty is peering into dark, dust-shrouded clouds to see the embryos of newly formed stars. Herschel has shown that even within the coolest, darkest clouds of our galaxy, matter is in motion, like a vast cloud of billowing smoke. Herschel has also cast its gaze beyond the Milky Way to our nearest galactic neighbor, the Andromeda Galaxy. In this view, we see Andromeda first through visible light, with its bright stars and dark lanes of dust. But with Herschel, the stars fade to black, and the dark dust shines like brilliant ribbons. Infrared telescopes are beginning to probe the most distant corners of the expanding universe, where light from rapidly receding galaxies is shifted to longer and longer wavelengths. In the future, infrared telescopes will be crucial as astronomers continue to peer farther and deeper in search of the very first galaxies and the first stars. But even farther down the spectrum, where infrared light transitions into radio waves, astronomers have found a signal that announces the beginning of the universe itself. That signal which comes to us from every direction in space, first showed up by accident in a horn-shaped antenna operated by Bell Labs in New Jersey. Two researchers, Arno Penzias and Robert Wilson, made the discovery in the mid-1960s, not far from where decades earlier, Carl Jansky first detected radio waves from the Milky Way. Without realizing it, Penzias and Wilson had discovered the cosmic background, light that was emitted by our universe when it was filled with white-hot gas in the aftermath of the Big Bang, nearly 14 billion years ago. Today, satellites are probing the cosmic background and mapping its features in detail. These small variations in wavelength and temperature can reveal volumes of information about the physical properties of the early universe, and may eventually help us understand what caused the Big Bang. "400 years ago, astronomers first turned the telescope to the heavens and discovered there was more to the sky than meets the eye. Now, a host of new eyes in space, as well as radio ears on the ground, have opened up the entire spectrum, giving us a cosmic rainbow of perspectives as we try to piece together how the universe works." It's not just what we see that has changed over the course of this incredible journey, but the idea of seeing itself. Of all the places on Earth where humans can feel close to the heavens, none can beat the rocky desolation of Chile's Atacama Desert. Here, where rarely a cloud is seen, peak after towering mountain peak thrusts into the dry, still air. And each night, as darkness descends, the stars shine with an unblinking clarity that rivals the view from space itself. Once nothing more than a distant curiosity, this harsh and remote landscape has become the focal point for some of the most exciting developments in our exploration of the universe. And there is much more to come. Today's state-of-the-art telescopes are larger and more expensive than ever. So to get the most out of them, astronomers want to put those telescopes where they can be used to their best advantage. The Atacama offers just such a place. It's the driest desert on Earth with only a handful of cloudy nights each year. The airflow is remarkably steady, and it's far from cities and towns that throw light into the night sky. Put it all together, and you have a gateway to cosmic discovery. Today, Chile is home to some of the world's most impressive observatories. And here, high atop Cerro Paranal is the most impressive of all. This is the VLT, short for Very Large Telescope. Despite its name, it's actually 4 large telescopes, plus 4 smaller ones, which can either work independently or together, like a giant light-collecting machine. Part of the secret to the VLT's success is its location. Perched more than 2.6 kilometers above sea level, Cerro Paranal boasts the ideal atmospheric conditions for astronomy. But there is more than an exceptional sky at work here. To produce views that challenge the Hubble Space Telescope for beauty and clarity, the VLT also relies on some exceptional technology. It starts with each of the 4 large telescopes' main mirrors. Each one is a single piece of aluminum-coated glass 8.2 meters across, but less than 20 centimeters thick. Such a large but thin mirror would naturally bend under its own weight. To prevent that from happening, the VLT employs a strategy for keeping its 4 giant mirrors in shape. Each rests on a bed of 150 pistons, called actuators, which can press on the mirror at different points. The actuators bend the mirror by just the right amount to maintain its ability to focus, no matter how the telescope is moved or tilted. Such precision is perfect for roaming the rich star fields of the southern Milky Way. Here, like a bubble frozen in time, the VLT spies the Dumbbell Nebula, a ballooning cloud of gas made up of the outer layers of a dying star. Nearly 20 times farther away, the VLT finds a burst of celestial fireworks in mid-eruption. The largest and brightest stars in this cluster would outshine our sun 8 million times over. These images are all the more breathtaking because they are taken from Earth, not from space, by an observatory that is swimming in air. Even on the clearest of nights, unseen turbulence in the air pushes starlight around as it journeys through Earth's atmosphere. The same effect is what makes the stars twinkle. To get around this problem at VLT, all the light gathered from each telescope's main mirror is bounced onto a second mirror, which can rapidly deform to reverse the distortions caused by the moving air. Like other observatories in Chile, the VLT is in a perfect position to put its cutting-edge technology to use. In the northern hemisphere, the central regions of our Milky Way galaxy can barely be seen above the horizon. But in the south, the galactic center arches high overhead. Shrouded behind dark ribbons of interstellar dust, the center of the Milky Way is an elusive target. But the telescopes of the VLT can also detect infrared light, which can pass through the dust. In this unprecedented image, the VLT has revealed the spectacular concentration of stars at the heart of our galaxy. Here, dozens of giant stars crowd a region that is only 2 light-years across. Astronomers can now return to this view again and again to see the stars moving as they orbit the giant but unseen black hole lurking at the heart of the Milky Way. In every journey, there is always another mountain, another spectacular view. What we will find, we do not know. What we do know is that in the journey to explore the cosmos, our path leads through the Atacama. By night, the skies over Chile's Atacama Desert offer a dazzling spectacle. Some of the best views of our universe found anywhere in the world. By day, the stars fade away, and the giant telescopes on their mountain perches retreat into their domes, shunning the harsh southern sun. Yet, even in broad daylight, there is still plenty of universe to explore. Radio waves reaching the Earth from the depths of space carry information about distant events in our galaxy and far beyond. For years, radio astronomers have been scanning the skies with giant dishes and picking up the faint signals that come from sources all over the universe. But there's one frontier left to conquer. Astronomers call it the submillimeter. That just means radio waves that are very short, less than 1 millimeter across. It turns out some of the most interesting phenomena in the universe, from the births of stars to the most distant galaxies, are giving off energy at those wavelengths. But there's a problem. Water vapor in Earth's atmosphere is very good at blocking submillimeter waves. So, to see the universe at those wavelengths, astronomers need to go to one of the highest and driest places on Earth. And that place is here, 5 kilometers above sea level. Nestled among the high peaks of the Andes Mountains, astronomers are building the Atacama Large Millimeter Submillimeter Array, ALMA for short. When completed, it will be the largest and most sophisticated radio observatory on Earth. At its heart, ALMA consists of 66 large dish antennas, some built in Europe, some in North America, and some in Japan, reflecting the international partnership behind the project. Each dish is a nearly perfect parabola, precisely tuned to pick up signals at submillimeter wavelengths. Each dish on its own would be an impressive tool for exploring the heavens. But at ALMA, the dishes will work together as one, creating a giant, steerable receiver that will probe the skies with unprecedented sensitivity, gradually building up a view of the universe as we've never seen it before. One of ALMA's highest priorities will be exploring the complex tangle of interstellar gas and dust that spans the plane of our Milky Way galaxy. In doing so, it will not only witness the formation of stars, but in some cases, it will discern young planets emerging from the debris that surrounds those stars, something that happened in our own solar system 4.5 billion years ago. To satisfy the variety of groundbreaking observations that astronomers hope to make with ALMA, the array needs to have more than just a large number of dishes. It must also be able to change the arrangement of its dishes depending on the kind of observation that is being made. For some targets, ALMA will work best if most of its antennas are clustered towards the center of the array. At other times, they will need to be much more spread out to increase the precision of the entire array. At its widest configuration, ALMA's antennas will be spread out over 14 kilometers. Moving these antennas around will not be easy. Each one is a high-precision scientific instrument that also happens to weigh about 100 tons. To do the job, ALMA has two special transporters, as massive and muscular as they are maneuverable. The transporters feature 28 independently controlled wheels and can move fast across the high desert roads. But in practice, when one of ALMA's antennas is being transported, the driver will aim for a gentler ride. The ability to adjust the locations of its antennas is just one way in which ALMA will optimize its view of the heavens and bring a new level of detail to our exploration of the distant universe. Because ALMA will be able to zero in on small and remote objects, it will be perfect for isolating and measuring the properties of very distant galaxies. Looking back to a time when the universe was less than 1/20th of its current age, and the very first galaxies were forming out of the residue of the Big Bang. By taking advantage of some of the most beautiful skies in the world, this incredible new observatory will help transport astronomers deep into the past. What they hope to find will answer some of our deepest questions about the origins of the universe. In one of the driest and most desolate pockets of Chile's Atacama Desert sits a maze of weathered rock formations, sand dunes, dry lake beds, and salt deposits that glint like snow in the desert sun. Here, more than anywhere, the otherworldly quality of Chile's extraordinary landscape seems at its most intense. This place is called Valle de la Luna, the Valley of the Moon. Tourists come to experience what it might feel like to set foot on another planet. In the 1990s, researchers came here to test an early prototype for a rover on Mars. The Atacama seems so much like it's part of another world. Perhaps it's fitting that now it's leading us to new worlds across the galaxy. At the VLT on Cerro Paranal, astronomers have zoomed in on Beta Pictoris, a nearby star easily visible to the naked eye in the southern hemisphere. For years, it's been known that a swirling disk of dusty debris surrounds Beta Pictoris. And more recent observations indicate that at the center of the disk, there's a gap, roughly the same size as the orbit of Saturn in our solar system. Astronomers suspected a large planet was responsible for the gap, because a planet's gravity would sweep that part of the disk clear of the dust and small chunks of debris that had coalesced around the newborn star. But finding such a planet is like looking for a very small needle in a very large haystack. In 2003, by using the VLT's infrared capability, astronomers were able to spot a faintly glowing dot located very near Beta Pictoris. It looked promising, so they waited. 6 years later, their suspicions were confirmed. By 2009, the object had moved to the other side of the star, clearly showing that it is a planet orbiting around Beta Pictoris. The planet is estimated to be 8 times more massive than Jupiter, not a place where we would expect life to emerge. But where one planet exists, there could be more. The Beta Pictoris system, located only 60 light-years from Earth, is just one more reason why astronomers are drawn to the southern hemisphere. By sheer chance, the night sky we see below the equator is particularly rich for stargazers. For those used to the more subdued skies of the north, a first glimpse at the southern Milky Way, with its vast star clouds and dark tendrils of interstellar dust, is simply awe-inspiring. Taking a cue from the scientists at the great observatories, more and more backyard astronomers are now coming to Chile for a chance to glimpse what they cannot see in the north. Here, even a quick scan with binoculars can offer rewarding views of the region's signature constellation, the Southern Cross. Elsewhere, an ordinary digital camera can bring out the subtle colors in the glow of ionized gases where new stars are forming. Like their professional counterparts, the amateur astronomers who come to Chile have found that technology can help them get the most out of the view. For example, the movement of air will cause an image to blur slightly, no matter how good the seeing conditions. But by taking hundreds of images of the same object and then digitally combining them, it's possible to create images of astonishing clarity. Here, the method is used to bring out fine details in the Eta Carina Nebula, one of the great spectacles of the southern sky. Humans have been looking at the stars since before written history and exploring the universe with telescopes for centuries. But it may be that nowhere on Earth have humans found such a strong connection to the night sky as in the Atacama. It truly is a stargazer's paradise. Perhaps it requires being in a place that is far removed from earthly affairs to see the possibilities that lie beyond our own world. With each generation, we have seen farther and encountered wonders greater than we can imagine. From the barren rocks of the Atacama, the path now leads deep into the galaxy. We do not know if our descendants will ever venture to the stars, but should they step away from Earth's embrace, we can, from here, begin to see the way. In the Atacama, we stand poised at the cosmic doorway. What lies beyond is the road to cosmic infinity. In a world of change, the night sky has come to signify all that is eternal. Seasons may pass. Civilizations may rise and fall. But the stars still traverse the heavens each night in a timeless celestial procession. So steady is the light of the stars that the constellations we see each night are the same ones our ancestors gazed upon thousands of years ago. And each individual star could shine for millions or billions of years more. The stars and galaxies convey the impression that the things we see in the universe are permanent and unchanging, at least over the course of a human lifetime. But that's not always the case. One of the most astonishing phenomena in the night sky is so fleeting that most people have never seen it, even though it's very common and can easily be found without a telescope. For generations, the aurora borealis, or northern lights, have enchanted those lucky enough to see them. With their bright colors and strange, wavering movements, the auroras seem to be alive with a supernatural energy, a perception that arises again and again in stories from the past. In North America, for example, the Algonquin people explained them as the light reflected from the campfire of the Creator. While to the Vikings of Scandinavia, they were the Valkyrie, supernatural beings who accompanied fallen warriors on their way to meet the gods. And in many northern cultures, they are simply regarded as the spirits of the ancestors, dancing in the sky. But it was the astronomer Galileo in the 1600s who first named these events aurora, after the Roman goddess of the dawn. Galileo incorrectly speculated that auroras were reflections of the sun's rays. But he did get one thing right. It is the sun that is ultimately responsible for the aurora. It would take 3 more centuries before Christian Birkeland, a Norwegian scientist, hit upon the correct explanation. The aurora, it turns out, are the result of billions of microscopic mid-air collisions. Starting at around 250 kilometers above Earth's surface, electrically charged particles from the sun collide with the oxygen and nitrogen atoms and molecules in our atmosphere. The gases are energized by these collisions, giving off a colorful glow. The different colors relate to the height, energy level, and type of gas. For example, oxygen can glow both red and green, while energized nitrogen can produce a blue or crimson color, or sometimes both at once, which makes the aurora seem purple. The solar particles responsible for all this energizing can be seen most vividly during a solar eclipse. As the moon slips in front of the sun, the blazing light of the sun's surface is temporarily blocked. As the sky goes dark, a feathery glow appears around the silhouette of the moon. This is the solar corona, a region where particles blasted off the sun's surface are heated to extreme temperatures and eventually driven outward into space. As they travel, the solar particles form an invisible current called the solar wind, which blows past the planets of our solar system on its way to the stars. As As the solar wind flows past Earth, some of the particles are captured by our planet's magnetic field, which is generated deep inside Earth's core. Like tiny compass needles, they follow the lines of magnetic force heading down to our planet. The magnetic field lines converge near the north and south poles. The aurora they produce are mostly seen far from the equator, closer to the Arctic and Antarctic regions of our planet. Sometimes auroras are dazzling and brilliant, and other times they do not appear at all. The secret to why auroras are sometimes spectacular and sometimes scarce lies again with the sun. The more active the sun, the more potent the solar wind, and the more beautiful the auroras. Like Earth, the sun has its own magnetic field, but the sun's is more powerful and it originates within the hot plasma deep in the interior. The most obvious signs of the sun's magnetism are sunspots, dark patches that appear where lines of magnetic force have broken through the surface. Regions associated with sunspots can be incredibly dynamic, sometimes spawning massive explosions called solar flares, which can release more energy than the detonation of 1 million nuclear bombs. An active sun is also more prone to coronal mass ejections, magnetized bubbles that can grow within the sun's corona and ultimately burst outward, sending billions of tons of energized particles racing through space, turning the steady flow of the solar wind into the equivalent of a hurricane. If such an event happens, within hours, high-speed particles are battering Earth's magnetic field. Down on the ground, the effect is often a spectacular display of aurora. But there are other effects. Violent fluctuations in the Earth's magnetic field can overload power lines and cause blackouts. Because of their potential to disrupt technology on Earth, solar storms are the subject of intense study. That means the aurora have now stepped out of myth and legend to become part of a larger space laboratory, helping us to understand the sun and its influence on our planet. The aurora may be a phenomenon of our atmosphere, but it is directly connected to forces at work far off in outer space. Perhaps it's fitting, then, that we have to go to space to understand it best. Like a delicate sculpture suspended in silent grace, the International Space Station sails over our planet. The station is humanity's most ambitious outpost. It lies only a few hundred kilometers above Earth's surface, yet it is our beachhead into the infinite vastness beyond. With the station, we now have a perpetual eye on our planet from above, a way to see Earth in all its glory, including oceans, continents, and our best views yet of the Earth's colorful aurora. Until the arrival of spaceflight, we really had only one place from which to view the aurora, down on the ground. That's changed now, and so has our understanding of what's really going on when the sky is on fire with northern lights. When it comes to the aurora, it turns out that space is the place to get the big picture.
4,
1, 0.
In 2007, NASA's Themis mission probed the forces that can turn a calm aurora at the poles into an all-sky light show with potentially paralyzing consequences for our technology. 5 microsatellites measured electric and magnetic fields in space, as well as the flow of solar particles during an aurora. At the same time, an array of 20 ground-based stations in Canada and Alaska took wide-angle shots of the aurora while making magnetic measurements. Themis revealed that the energy contained in just one solar storm is equivalent to that released in a powerful earthquake. The mission also found invisible strands of Earth's magnetic field dangling 40,000 kilometers out into space. Called magnetic ropes, these ephemeral fields capture solar wind particles, briefly tying the Sun and Earth together until the ropes unwind and dissipate. A parallel project, Europe's cluster mission, involves 4 identical satellites orbiting the planet in formation. Their goal is to provide a 3-dimensional picture of how the solar wind interacts with the Earth's magnetic field and produces aurora. Like mapping an electromagnetic landscape, Cluster is helping determine exactly how particles that originate at the Sun gradually find their way down into our atmosphere. These studies from space remind us that auroras are a planet-wide phenomenon, and they should arise wherever the same 3 ingredients occur anywhere in our solar system. Those ingredients include the flow of particles from the solar wind, a planet with a strong magnetic field, and a dense atmosphere for the solar particles to collide with. The planet with the strongest magnetic field in our solar system is Jupiter. A giant ball of gas so large, all of the other planets would fit inside it. Jupiter would seem like a prime spot to search for auroras beyond Earth. Even at a distance 5 times farther from the Sun than Earth, Jupiter's intense magnetic field is strong enough to pull in the solar wind. Io, the closest of Jupiter's large moons, sports its own magnetic field. Gas in its atmosphere glows, causing a small aurora of its own. This field affects particles caught in Jupiter's magnetic web, funneling them toward a specific spot in the giant planet's atmosphere, creating a bright spot in the aurora that changes position with Io. Fainter spots in Jupiter's auroras are believed to be the footprints of Ganymede and Europa, 2 more of Jupiter's large moons. Saturn is another gas giant in the solar system with auroras. First captured in one of the Hubble Space Telescope's early images, these auroras are now monitored by the Cassini spacecraft currently orbiting Saturn. Hubble and Cassini both found auroral ovals around Saturn's poles, but glowing in ultraviolet light. Later, Cassini found a whole new set of auroras glowing in infrared. This aurora, unlike any other before seen, covers the pole rather than crowning it like a glowing ring. The ability to explore the other planets in our solar system has shown us that auroras are not a phenomenon unique to Earth. Anywhere where a moon or planet with a gaseous atmosphere and a strong magnetic field is exposed to the relentless tides of the solar wind, we should expect to see something like the Northern Lights. And now, with technology on our side, it's possible to enjoy these dancing lights as never before. The aurora borealis have inspired our stories and filled our dreams since long before the beginning of recorded history. Yet our efforts to adequately record and study these colorful, moving lights in all their ethereal beauty have always fallen short, until now. Today, the advent of digital photography makes it possible to capture the faint and ever-changing light from the auroras. Now, backyard stargazers around the world are putting these tools to use and showing us what until now only a few were lucky enough to witness. An aurora we see from the ground is part of a larger structure in the form of two large ovals centered on the north and south magnetic poles. To see auroras regularly, you have to be under one of these auroral ovals, or at least close enough to catch a glimpse. That means people living in the far north or south have the best chance to see auroras on a regular basis. When there are more particles flowing toward Earth, the ovals expand, covering a larger area and making auroras visible nearer the equator than usual. Observers at latitudes closer to the equator will only see the highest auroras, which appear as a reddish glow in the direction of the poles. In some cases, auroras hang like curtains above the Earth. This is because Earth's magnetic field traps particles from the solar wind and channels them almost straight down. They cannot wander away from the field lines, so from a distance, we see them as sheets of light. Some of the most spectacular auroras of all are those that occur when these shifting curtains of light are directly overhead. They create the effect of radiating lines of moving light, pulsing and emanating from a central point. Such displays are breathtaking, and they ensure that no matter how well we come to understand auroras, we will never cease to be filled with wonder when we see them. When you stop and think about it, no other process in nature so directly connects something that's happening deep beneath our feet in the core of the planet with something that's happening inside a star, our sun. But there's also another way that the aurora may connect us here on Earth to the larger universe that we're a part of. Because they are a product of Earth's magnetic field, auroras are a visible sign our planet is largely protected from the bombardment of particle radiation that would otherwise be raining down on us from space. By deflecting and channeling many of these particles toward the north and south poles, the magnetic field acts as a shield, making the Earth's surface safe for life as we know it. Although today we are far from being able to observe other Earths directly, astronomers are now beginning to test the idea that we might someday be able to detect the energy of an auroral display underway on another world beyond our solar system. If such a detection could be made, it would come with some big implications. It would allow us to distinguish between a planet like Earth and similarly sized planets like Venus, which has no magnetic field and is completely inhospitable. In fact, the presence of auroras on another planet would be our cue to look for signs of life. Mysterious and beautiful, intriguingly complex, we have now come to realize that the auroras that light up our night sky are also a colorful calling card that advertises our existence. Perhaps the auroras of another world will one day help lead us to our first meaningful contact with other conscious beings in the universe, and point the way to a cosmos full of light and life. The universe engages us with both its unending vastness and its rich diversity. The farther we look, the more we discover, and the more we realize how much there is yet to understand about the cosmos that surrounds us. The challenge for astronomers is that our view only extends so far. Our technology allows us access to a finite part of an infinite reality. Physically, we are bound to the Earth and the nearby worlds of our solar system. With our observatories, we can only see the light that happens to come our way from the stars and galaxies. How then can we hope to explore the parts of the universe we can't reach and can't see? Fortunately, there is a way. One that doesn't just enhance our senses, but enhances our ability to imagine the universe in a virtual way. Once, there was only one way to explore the distant universe, through the eyepiece of a telescope. But times have changed. Astronomers can now turn to their supercomputers to conjure up representations and simulations of what goes on in reality in order to see and understand reality better. Along the way, they've created something that's close to a new kind of art, the art of cosmic visualization. As a starting point, computers can help transport us to where we can have a new and better vantage point on places we've already explored. One such place is the Moon. Humans have not set foot on its desolate surface since 1972. Since then, many robotic spacecraft have orbited our satellite, taking countless images and sending back a torrent of topographic and mineral data. Most recently, scientists have obtained some of their best views of the Moon with NASA's Lunar Reconnaissance Orbiter, LRO for short. LRO carries a powerful camera as well as an altimeter, which bounces laser light off the moon's surface and measures the time it takes to reflect back to the spacecraft. Together, this information can be assembled in a computer to provide a three-dimensional perspective of lunar craters and mountains, bringing us much closer to the surface than the spacecraft actually traveled. What is most astonishing about this particular flyover is that, although it looks very realistic, no astronaut has ever seen this part of the moon. And scientists are interested in finding out more. These views are not simply aesthetic choices. They are created to help planetary scientists better understand the complex history of the moon's ancient surface and identify future landing sites where rovers or astronauts may one day unearth a deeper understanding of our nearest neighbor in space. After the moon, humanity's next step into the great beyond could well be Mars. No planet apart from our own has been the subject of such intense scrutiny and the destination of so many robotic missions. In recent years, it seems an entire fleet of spacecraft has descended on Mars, either roving over its terrain or imaging its surface from orbit. Like its lunar counterpart, the Mars Reconnaissance Orbiter studies the planet from high above. But this computer-simulated flyover, created with data from the spacecraft, makes it feel like we're staring out of the window of a Martian airplane. Traveling to Mars would present the biggest challenge humans have yet faced in space, and it is still far from routine for the robots blazing a trail here. Lots of data is key to planning an effective exploration. Even for an unmanned rover, it is crucial for researchers to know what is waiting for their vehicle before it sets down on the planet's surface. Here, information from Mars Reconnaissance Orbiter has been turned into an in-depth tour of Gale Crater, now selected as the landing site for Curiosity, the next rover to be sent to Mars. The crater reveals an intriguing landscape. Sections of its floor are covered with ancient sediments that may have been deposited long ago by flowing water. At the center of the crater is a towering mountain, 5 kilometers high. How it came to be there is unknown, but its layers of rock were laid down at a time when Mars may have been warm and wet enough to support life. Researchers hope views like this will help them chart an optimal surface route for Curiosity's challenging mission. In a completely different way, astronomers have used computers to obtain a three-dimensional view of the Orion Nebula, one of the nearest and most spectacular star-forming regions in our galaxy. Here, the computer allows us to travel many times faster than the speed of light, flying around the cluster of bright stars at the heart of the nebula. These stars illuminate the hydrogen and other gases within the nebula, making them glow. They also drive back the gas with a strong stellar wind, which creates a hollow space inside the nebula and exposes the embryos of new solar systems in the midst of formation. such views are both artistic and scientifically accurate. But they merely scratch the surface. The real power of computers involves not just exploring new landscapes, but in revealing the hidden forces at work in shaping our universe. The roots of astronomy lie in our attempts to keep time. Patient skywatchers once used the stars to divide the night. They tracked the sun's yearly trip through the stars by watching the constellations appearing out of the sunset and fading into the dawn. Now, the arrival of powerful computers is allowing astronomers to deal with time in a new way. The real power of supercomputers in astronomy is not simply to show us what the universe might look like in places that are too hard for us to get to. It's to show us how things change over vast timescales that we could barely comprehend, let alone experience. In that way, a computer can be like a cosmic clock. Just set it running and see what kind of solar system or galaxy or universe takes shape. Astronomers have long thought our solar system formed out of a disk of debris that swirled around the newborn sun 4.5 billion years ago. When we peer with telescopes at star-forming regions elsewhere in our galaxy, we can find evidence of disks around other young stars. But how exactly did it happen here? And how did it lead to the family of planets we recognize as our solar system, including one planet, Earth, that ended up in just the right place to support life? Because we can't go back in time to see how we got here, astronomers use the information gleaned from observing other stars to set up computer simulations of our solar system's formation. Such simulations offer a virtual laboratory to test detailed theories of what really happened. Astronomers have had some success modeling solar systems, but can we turn the clock back even farther to simulate the birth of galaxies? According to current theories, the galaxies we see today formed from smaller galaxies, created when the first stars died and left behind black holes that act like cosmic glue. The black holes came together, creating cores around which larger galaxies formed. As we see, galaxies did not form in isolation. Often, many formed in the same part of space, gathered in clusters and superclusters. In some cases, two galaxies may run into each other. This can be a gentle collision, a cosmic fender bender in which the vast distances between the stars in each galaxy means they pass right through each other, distorting only slightly due to their mutual attraction. In other instances, simulations show how celestial fireworks can occur, with galaxies smashing into each other, exploding, and recreating in a completely new form. As we look around the sky, we see many examples of interacting galaxies. And now, supercomputers are helping us turn time backwards to see how they got that way. Even our nearest galactic neighbors are in the process of interacting. The Andromeda Galaxy is 2.3 million light-years away. Through a telescope, it's also possible to see a smaller companion galaxy. Modeled here, with each star represented as a point, we see the two galaxies engage in a long, slow, gravitational waltz. According to this simulation, the dance leaves a big impression on both galaxies. But, as is usually the case, it is the smaller partner that is more obviously affected by the gravity of its larger neighbor. Our own Milky Way is smaller than Andromeda, and observations reveal that we are also on a collision course with this galactic monster. Flashing forward billions of years into the future, we see the fate of our own galaxy is to collide and ultimately to merge with Andromeda. Will this affect our planet? It's hard to imagine that it will not. By then, Earth will be into its old age and very likely no longer a habitable world for humans or anything like us. But here, with the help of a computer, we can see how the future will play out far beyond the boundaries of our own experience. After centuries of scanning the skies with telescopes and decades of sending unmanned probes to other planets, we should know our own solar system pretty well. But we can't see everything. For example, we know the formation of our solar system should have spawned a zone of small icy bodies well beyond the orbit of Neptune. Pluto, discovered in 1929, may simply be one of the largest members of this group, collectively known as the Kuiper Belt. Since 1992, many dozens of Kuiper Belt objects have been discovered, and estimates suggest there could be up to 70,000 more. Now, a computer simulation can help show us how the Kuiper Belt may appear to an infrared telescope observing our solar system from a distance. It appears as a glowing ring because collisions within the belt create dust which radiates a faint infrared light. A gap in the ring reveals the presence of a planet. In this case, Neptune. Scientists can also take the simulation backward in time to see how the Kuiper Belt is likely to have changed over billions of years. Eventually, it devolves back to a simple ring, exactly what's been found surrounding some other stars that are much younger than our Sun. The computer is our gateway to understanding the hidden influences at work in the cosmos. The ultimate hidden influence is the influence of dark matter. Discovered through its gravitational pull on stars and galaxies, dark matter gives off no light and is not directly observable by any other means. A lump of dark matter would pass through Earth like a ghost, since it does not interact with ordinary matter at all. Yet the dark matter in our universe outweighs normal matter by 5 to 6 times, and its gravitational pull has had a profound effect on the way the universe has evolved. Using computer simulations, we can now imagine what it would be like to fly through our own galaxy and experience it as though we were wearing dark matter glasses. The effect is something like driving through a snowstorm, but on a galactic scale. In this visualization, everything made of atoms, including stars and planets, have been rendered invisible. What we see is only dark matter, which the computer shows us forms in countless clumps that orbit around the galaxy's center. Over the course of our solar system's history, Earth may have flown through many of these clumps, but we would never know this. However, the presence of this dark matter guides how the stars move and shapes our galaxy. The effects of dark matter grow even more significant as we look to larger scales. For example, when we peer out to the universe over hundreds of millions of light years, we find the galaxies are not distributed randomly. Instead, we find there is a pattern to the way the galaxies are organized. Astronomers call it the cosmic web. Matter has tended to concentrate, and galaxies have tended to form in sheets and filaments, leaving surrounding voids or bubbles where matter is relatively scarce. What is the source of this cosmic web? With the help of supercomputers, astronomers have been able to determine the answer. When dark matter is added to the equations that show how the early universe took shape under the influence of gravity, it is the cosmic web that emerges. There's no question that the use of supercomputers has both broadened and deepened our knowledge of how the universe works, and that computer simulations have allowed us to travel through time and space in a virtual way so that our minds can go where our bodies cannot follow. The best part is this is just the beginning. Supercomputers are only getting faster and better, and that means the virtual universe that's opening up before our eyes is probably going to be even more imaginative and spectacular. Perhaps there's an even deeper insight we can glean from the new power of computers and the way they are being used to help us understand nature at the largest scale. What these simulations tell us is that the cosmos is inherently mathematical in nature. Whatever our universe is, and however it came to exist, it is governed by numbers and relationships that can be represented in a computer. The universe is not getting smaller or easier to understand, but with computers to aid us in our future explorations, we know that much, much more of it will now be within our grasp.